Hey everybody. Today we're talking about confidence intervals for proportions. A confidence interval for a population proportion p is computed using this formula, where p hat is the proportion of successes in the sample, z star is the critical z value that comes from your level of confidence c, and n is just the sample size. So in a sense, this confidence interval really is just sort of plug and chug. On the other hand, the human doesn't add any value over what a machine can do if all we're doing is plugging in, so it's really important that we back up and understand this confidence interval formula a little bit better. So a proportion is really just a particular sort of average, or mean. You add up the total number of successes, you divide by the number of trials, that gives you your proportion. And the central limit theorem describes the distribution of any kind of sample mean x bar, including a sample proportion p hat. Quick refresher on the central limit theorem. Suppose simple random samples of size n are drawn from a population with mean mu and standard deviation sigma. Now, this population could have any shape whatsoever. It doesn't necessarily have to be bell-shaped. If n is large, then the sampling distribution of the sample mean is approximately normal, so it does have a shape that we know something about. Furthermore, the mean of the sampling distribution of x bar is mu, and the standard deviation is sigma divided by the square root of n. Notice the phrase n is large as a condition on this theorem. That's pretty vague. We will talk a little bit about how large is large enough in just a minute. Going back to proportions, if each of our n observations is coded as 0 for failure and 1 for success, so that is like a Bernoulli random variable, then the mean and standard deviation of any particular observation, xi, are p and the square root of p times 1 minus p, respectively. I have a whole vid on Bernoulli random variables and the binomial distribution more generally, where this is computed and explained with a little bit more patience. I'll throw a link to that up top. Applying the central limit theorem and some of the theory that accompanies it, we know that the sample proportion p hat, the average of n such observations, has an approximately normal distribution with expected value of p and standard deviation of square root p times 1 minus p over n. Since we don't know the population proportion p when we're doing confidence intervals, we do the obvious thing, which is to estimate it with the sample proportion in that formula. When we do that, we get the square root of p hat times 1 minus p hat over n. So that's supposed to approximate the standard deviation of the statistic p hat over many samples of the same size. We call this the standard error of the statistic p hat. And again, it describes the variability of p hat from one sample to the next. And that explains its presence in the formula for the confidence interval for the population proportion. You can see here p hat plus or minus z star times that standard error. As always, we choose z star so that the area under the normal distribution, the standard normal distribution, that is enclosed between negative z star and positive z star is c. And that value z star can be computed with a little bit of care using an inverse normal CDF function. However, there's only a few values for c that are in common usage, with by far the most common being c equals 95%. And so really you can just look up your z star once you know your c value. For instance, when c is 95%, the corresponding z star is 1.960. The next most common values for c are 90% and 99%, with z star values of 1.645 and 2.576, respectively. The central limit theorem for proportions is not perfect, but it is much worse for small samples. As a general rule of thumb, you should only use this confidence interval formula for that population proportion when the sample has at least 5 successes and 5 failures. Let's wrap up by doing one example. Researchers wish to determine what proportion of Americans owns a dog. So they contact 250 people at random, and they find 116 that do own at least one. Construct a 95% confidence interval for the population proportion. So this is a good place to pause the video and give this a try on your own before going forward and seeing my solution and my explanations. So in this case, p hat is 116 divided by 250, or 46.4%. So the total number of successes, the total number of people that do own dogs, divided by the total number of trials. we are going to use Z star is 1.960 because we have a confidence level of 95%. So I'm plugging in that p hat, I'm plugging in that Z star, I'm plugging in n equals 250. Simplifying with a little bit of arithmetic, ultimately I get 0.464 plus or minus 0.062. So with 95% confidence, the proportion of Americans that owns a dog is between 40.2% and 52.6%. And I got those numbers by taking 46.4% and subtracting 6.2%, and then doing 46.4% plus 6.2%.